Welcome back. So now that we've defined relative atomic mass in terms of what it means and reviewed isotopes, we're going to look at calculations relating to this and how we use the data that we obtain from a mass spectrometer to calculate the relative atomic mass of an atom using that weighted average of all the isotopes that are present. So with relative atomic mass, we give it the symbol AR. Okay, and this is typically relating to a specific element. We will calculate for compounds later, but when we're doing these calculations, we're talking about the relative atomic mass of an element, and we calculate it from measurement of the percentage abundance of the relative isotopic masses, i.e. we use the mass spectrum or the data table from a mass spectrum to know the isotopic masses and their percentage abundance in order to calculate the overall relative atomic mass. It is the weighted average of its naturally occurring isotopes, where carbon-12 has a mass of 12 units exactly, and we report this in the units of IM2 or atomic mass units, which have no physical correlation. They are just a measure of how much each element the size of each or the mass of each element in relation to each other. The formula that we use is that the relative atomic mass is equal to the sum of their isotopic masses multiplied by the relative abundance divided by the relative total abundance, or essentially 100. So we're going to take our isotopic mass from the mass spectrum, multiply it by the percentage abundance that it has, so 75% or 85%, and then we're going to divide by the total abundance, which for anything in a percentage is 100. As we've mentioned, the percentage abundance of each isotope is always constant in nature. So for hydrogen, 99.9860% of hydrogen is present in the universe as hydrogen 1. We get 0.0140% of deuterium, which is hydrogen 2, and we get even less tritium, which is hydrogen 3. That proportion is fixed. It doesn't change in our naturally occurring isotopes. For chlorine, we have two isotopes. This is chlorine 35 and chlorine 37. Chlorine 35 makes up 75.8% of the chlorine that we find, and chlorine 37 makes up 24.20% of what we find. So let's have a look at these calculations. What we're going to do, this is data that was obtained from a mass spectrum for magnesium. So this mass spectrum would have three peaks, one at 24, one at 25, and one at 26. Okay, and the percentage abundances, so the height of these peaks relative to each other, would be 78.7%, 10.13%, and 11.17%. So we're going to set up our calculation where the relative atomic mass of magnesium is equal to the relative isotopic mass, 23.99 in this case, multiplied by its percentage abundance plus the other isotopes, 24.99, multiplied by its relative abundance, then our 25.98 multiplied by 11.17, and this is all going to be divided by 100. So if we plug that into our calculator, 23.99 multiplied by 78.7, and then we're going to add 24.99 multiplied by 10.13 and 25.98 multiplied by 11.17, and then we're going to divide all of that by 100, and we will get our final answer. Hopefully, if you type that into your calculator, your final answer would have come out at 24.3135, which in the right number of significant figures, we have 4 significant figures here, is going to be 24.31. So relative atomic mass has no units, or we give it the units of IMU. So that's basically one where we take the data from a table and apply the formula. Let's move on to our next type of question. Now we can see here that the data hasn't been provided for us in a table, it's provided as a mass spectrum. It's that series of lines on a graph where we have the y-axis being the percentage abundance and the x-axis being the mass to charge ratio. So this is germanium, we've been told here, and we're asked two questions. To write the formula or the nuclide symbol for the heaviest species of germanium in the isotopic profile. So when it talks about the isotopic profile, it's referring to the mass spectrum. It wants the heaviest one, so we're going to move, if we can see here, the numbers are getting bigger as we go from left to right. So that will be this isotope here, which is going to be 76. Okay, so for this, we're going to need to know the atomic number of germanium, and then we're going to write the nuclide symbol with the atomic number and the mass number for this particular isotope. So checking our periodic table, we will see that germanium has an atomic number of 32, it's element 32. And now we want the heaviest isotope, so that's going to be germanium 32, our atomic number at the bottom, and we said that 76 was the mass of our heaviest isotope. So part B wants us to use the percentage abundance for each isotope and calculate the relative atomic mass of germanium. We have 5 isotopes of germanium, so this is going to take a little bit of calculation. So we're going to calculate the relative atomic mass of germanium, and we're going to do exactly what we did before. We're going to take our isotopic mass, so the first one here is 70, and just putting that in brackets. So we're going to take 70, and we're going to multiply by our percentage abundance, which is 20.6. Then we're going to add our next isotope, which is 72, reading from the graph along the horizontal axis, multiply by 27.4. The next one is going to be 73. And we're going to multiply that by 7.7. And then we're going to add in our 74, quite a long one this one, and multiply by 36.7. And then our last one, which is going to be 76 multiplied by 7.6. And then we're going to divide all of that by 100. So have a go, put this into your calculator and check the answer when you return. Okay, so hopefully you came up with 72.70 atomic mass units for the relative atomic mass of germanium. Okay, we can see from this that the main isotope is our 71, 72, 73, 74, and 70. So this has brought our weighted average down to around 72 because our heaviest isotope is only 7.6% abundant. So we're sort of finding the average between these two, these three here would dominate the average. Okay, so they're straightforward, where we're given all the percentage abundances and we're given all the relative atomic masses and work from there. Sometimes the questions can be posed in a slightly different way, and we just need to remember that when we're dealing with percentages, all of the percentages need to add up to 100. So if we look at this example here, this is roughly about how tricky the questions get. So if you can do this one, then you're doing really well. What we're doing here is we're told that lithium has an elemental atomic mass of 6.941 units. So this is just saying IMU. And has 2 naturally occurring isotopes, lithium-6 and lithium-7. Okay, so this is actually giving us AR already. Their masses are 6.0151 AMU and 7.0160 AMU, respectively. So this one is lithium-6 and the other one is lithium-7. We're asked to determine the natural abundances to 2 decimal places. So we have 2 isotopes, and we know that the total of the percentage abundance of each one, so the percentage abundance of lithium-6 plus the percentage abundance of lithium-7 must equal 100. Okay, and we know that we have the formula AR is equal to the isotopic multiplied by the percentage abundance for both isotopes divided by 100. So what we can do is we can use algebra to help us solve this problem. If we say let the percentage abundance of lithium-6 equal X, then the percentage abundance of lithium-7 is going to equal 100 minus X. We can then substitute those into our formula. So we're going to take the values from the question. Our relative atomic abundance is 6.941. Then we're going to take the relative isotopic mass, so for lithium-6 is going to be 6.0151 multiplied by its percentage abundance, which we defined as X. And then we're going to add that to our lithium-7, 7.0160 multiplied by its relative abundance, which is going to be 100 minus X, so everything that isn't lithium-6, and we're going to divide all of that by 100. Now we're going to use essentially our mathematical skills to rearrange this equation and solve for X. So the first thing I'm going to do is multiply both sides by 100. So I will get 6.941 multiplied by 100. So I'll get my 694.1, and that's going to get rid of the 100 from the other side, is equal to 6.0151x plus, and I'm going to at the same time expand these brackets. So I'm going to get 7.0160 times x. That's going to this one here, so that's going to be minus, because I'm multiplying by minus x, and then I'm going to have my 7.0160 and multiply that by 100. So what I'll get here is 701.6. Now I'm going to gather like terms. I'm going to take this 701.6 over to the other side. So we're going to get 694.1, and we're going to subtract our 701.6, which is going to give me negative 52.5. And then I'm going to do the 6.0151 minus the 7.0160. So I'm going to have my 6.0151 minus 7.0160, and we're going to get that is equaling negative 1.0009, so essentially 1. So what we can see here is if we multiply, and that's x. So I'm going to divide both sides by negative 1.0009, so I'll get 52.5 divided by essentially 1 is going to be, x is going to equal 52.45%, because this is the percentage abundance of lithium-6. Okay, so the percentage abundance of lithium-6 is going to be 52.545, and then the percentage abundance of lithium-7 is going to be 100 minus 52.45. So we're going to have 47.55%. Okay, so in this case, we've defined our percentage abundance as X, and then we have defined the other one as 100 minus X. So if we're given the relative atomic mass and the mass of two isotopes, we need to use algebra in order to determine the percentage abundance depending on how many isotopes there are. So once we have that, you'll notice that the relative atomic masses that we've been calculating are very similar to the ones that we see on the periodic table. Essentially, the masses that are printed on your periodic table are the relative atomic mass for each element. So this means that if we want to know the relative atomic mass of a molecule or compound, we simply look up how many of each element is in the formula, and we add the masses of those individual atoms. As an example, we can find out the relative atomic mass of sodium chloride by remembering that this is Na plus and Cl minus, but the electrons make no difference to our mass. So we're going to look up sodium, and it'll be 22.99 off our periodic table, and then chlorine 35.45 from the periodic table. To find the relative atomic mass of sodium chloride, we simply add them together. Okay, and that's it. It doesn't matter how many atoms there are in the molecule. We just simply go through, work out exactly how many there are, what the relative atomic mass is for each one, and add it up until we have we've added up all the atoms in the formula. Just a quick note on isotopes, and we've mentioned this before. When we talk about isotopes being different, they are the same element. They have exactly the same number of protons. They only differ by the number of neutrons that they have in the nucleus. So this means that as far as we talk chemically in terms of chemical properties, isotopes will have the same chemical properties because they have the same number of electrons. They only differ slightly in physical properties such as density. Okay, so we can separate them using the mass spectrometer, but they are very, very similar and hard to tell apart. Okay, which is why when we talk about having a sample of carbon or a sample of oxygen, we don't typically specify whether or not it is all one pure isotope or another, because the compound itself will behave the same whether it is made up of the two naturally occurring isotopes of chlorine or just one. Okay, that's it from me. We will do a lot of practice on this in class, and I'll see you then.